going to tell us about volumes of definable sets and non-minimality. Patrick?
Oh, yeah, thanks for the invitation. Maybe I should start. I want to start. I don't know what this is, like a warning or something. So, oh no. Well, the real warning is that my pen might have stopped. Well, yeah, okay. Warning. It's not really a warning. So the thing is, this is a little bit weird to talk about because I guess I gave a talk on it in Vancouver about maybe 2 years ago, and then I talked to a few people about it, and every time I would talk to people about it, there's like a volume estimate that I was proving, and then they would listen to me and they would say, that just sounds like something that might be in the literature somewhere, and but like, so then I would go look, but it's kind of hard to find something that might be in the literature somewhere. Eventually, like I guess a few months ago, I decided to post it on the archive, mainly just because I mean, I like it. And within like a few hours, somebody pointed out a reference to the volume estimate from a couple of years ago, and then within like 4 or 5 days, somebody pointed out like a much older reference, and I'll tell you those references. In fact, it makes what I'm saying like kind of stronger, because my point is that the Peterzil Starchenko um, Gaga theorem follows from Bishop Stoll pretty directly. So maybe I'll write that down. My point is that the Peterzil Starchenko affine Gaga theorem has a relatively easy proof. I mean, maybe get rid of the word I mean, it has an easy proof using a hard theorem, which is Bishop Stoll, um, plus a simple volume estimate. And this volume estimate has been known actually for quite some time. Quite some time. So that's really the warning part, which is not reflected on the archive. In the archive version of this paper doesn't give references. Um, okay, so maybe having said that, let me just say what we're trying to do. So we want the idea is we want Gaga theorems. So we want Gaga theorems for possibly non-projective varieties. That saying that closed subvarieties, say of Cn, are algebraic. Saying that with suitable hypotheses. Closed subvarieties say of Cn, maybe I should say closed analytic subvarieties. Sorry, closed analytic subvarieties of, say, Cn are algebraic. Okay, and now we need hypotheses, which the following, I mean, it's kind of obvious that you need hypotheses, but this talk is a little bit about stating the obvious. So I might as well do that. So we need hypotheses. For example, I think the example that everybody thinks about is that the graph of z goes to just e to the z in C2 is a closed analytic, I guess, submanifold of C2, but it's definitely not algebraic. Yikes. And so recently, maybe I should say there's kind of a long history of, well, first, I guess, Kodaira, really, the embedding theorem, maybe the beginning of it, maybe that's not even the beginning of it, of proving that analytic sub-varieties are algebraic. But then I think also Borel's theorem about about maps to Hermitian symmetric, maps to locally Hermitian spaces is an example. And recently in Hodge theory, okay, two groups of people. So Bakker, maybe I'll write it in kind of so Bakker and Klingler or Brunebarbe and Tsimerman have used Affine GAGA theorem, have used an Affine GAGA theorem of Peterzil and Starchenko to reprove, so sort of mostly, some old results, so old results of Catani, Deline, and Kaplan. Well, maybe I'll list them. Catani, Deline, Kaplan on the Hodge locus. And then of me and Greg Perlstein and Kato, Nakayama, and Asui, and also Saito, I think. So Saito on the zero locus of a normal function. Okay, well, of a normal function. And they've also proved the conjecture of Griffiths, so and BBT. So that's Bakker, Brunebarbe, and Tsimerman. I think they've proved the conjecture of Griffiths on the image of a period map, saying that the image of the period map is algebraic. Proved a conjecture of Griffiths, saying that the image of the period map is algebraic. Okay, and I mean, I was interested in this because, first of all, well, this is very nice. I mean, really, I mean, it's incredible. The paper, I strongly recommend that everybody reads that. And But also these things are pretty nice too, because the proof is the proofs that they give of Catani, Delaney, and Kaplan, and of my theorem with Greg, and all these people on the zero locus of a normal function is also nice. The reason, let me just say the reason I say mostly, because in a way that's kind of the hidden motivation for the talk. So the take-home message for, say for Catani, Delaney, and Kaplan, is that the Hodge locus is algebraic. And this, similarly for my theorem with Greg, the take-home message is that the zero locus of a normal function is algebraic. But that's not what either one of us do. So either thing does. What we actually are showing is that the zero locus extends from a Zariski open submanifold to the closure. So in fact, in both cases, the heart of the theorem is on a polydisk, and we're showing that the zero locus extends from a punctured polydisk, a polypunctured disk, to the polydisk, and it's similar for Catani, Delaney, and Kaplan. So the Affine GAGA theorem doesn't really work that way. I mean, it wants to prove that something is algebraic. So part of what I was thinking about when I kind of thought about when I was writing this is that it'd be nice to kind of recover the output of the Affine GAGA theorem and the way that Bakker and Klingler, Brunebarbe, and Tsimerman work, but still get a purely a theorem that's not about like algebraic. It's not as tied to just things being algebraic. It's not as tied to the global situation. So the real thing is that Catani, Delaney, and Kaplan, and me and Greg, and all these people were all working like locally analytically on polydisks. So and on the other hand, the Affine GAGA theorem wants to work on affine variety. So I wanted to like square I don't know, to go to you know, to make it so it would work in the original setting. Anyway, so my goals for the talk are, one, to explain Peterzil and Starchenko. And that part of it is just that I really liked these papers, so I really got into the I mean, it was a way of me getting into O minimal things, and it's really nice setup. And then explain how to prove it using Stoll's theorem. And I was going to say the third goal was sort of talk about applications. And if I get to it, I'll do that. Actually, yeah. Okay, so maybe I'll leave here. So the first thing to say is what is, maybe we'll go to the next one. What is an O minimal structure? So this is so O minimal structures and Peterzil Starchenko. So, and I know, so there have been other talks here about O minimal structures. In fact, I watched one of them when I watched the recording of Abhishek Oswald's talk, which is really good while I was biking. So I hope I might repeat some of the things he said, but I mean, I want to make mine talk kind of relatively self-contained. So a structure is a collection of, I call it like, say, Sn from n equals 1 to infinity, where for each n, Sn, okay, is itself a collection of subsets of Rn, and they're called the definable subsets. Definable subsets of Rn. So this is a logic thing, obviously, and then it has to satisfy some axioms, and I always say I might forget some of them. So this class, this set Sn has to satisfy following axioms, plus maybe more if I forgot some. But I'll tell you where to look. So one, each Sn is a Boolean collection, so it's like closed under complements and unions. So each Sn is a Boolean collection. Let's write that. Number two is if A is in Sn, then A cross R is in Sn plus 1. Number three is if A is in Sn, then the set of x1 up to xn A, such that xi is equal to xj. That's also that's in S, and that's in Sn, actually. You have to think about that, but it's a subset of Sn. It's just you put two of them equal, but it's still a subset of Sn. And then four, which is maybe the most important, if A is in Sn plus 1 and pi from Rn plus 1 to Rn is a projection on a factor, then pi of A is in Sn. Okay, and now I'm going to say, now I'll just say that I might have forgotten some. So check with the really good book for this. So it is Van den Dries's book for the full list. And yeah, I mean, it's a superb book on minimal. Like almost everything that I say is a superb reference. So it's clear that setting Sn equal to the power set of R to the n, or if you want to, it's like 2 to the R n, gives you a structure. So for each n, gives a structure. So in which every set is definable. Okay, so it's also clear that the intersection, or should be clear, that the intersections of structures is a structure. Okay, so given a family of structures, given a family of subsets of Rn, not a family of structures, just a family of subsets of Rn, we can look at the intersection of all the structures containing the family. So given a family, let's say F of subsets of Rn, we can there's a structure, there's a unique smallest structure, let's say S, containing F, or maybe whose members contain F, whose elements contain F. So just namely the intersection of all structures containing F. Okay, and that's called the structure generated by F. Okay. So also, if S and T are structures and S contains T, then we call S an expansion of T. So if S and T, that's a bad T, T are structures with S containing T, then S is called an expansion of T. Okay, and the expansion, maybe some of this is a little bit boring, but you just have to say it. The expansion of T containing a family Fn of subsets of Rn is by definition the smallest expansion that contains the subset. So, yeah, okay, so the expansion of T containing a family, say Fn of subsets of Rn. So maybe n equals 1 to infinity. So n equals 1 to infinity. I think I don't want to write that in braces. I don't know if that's supposed to go in braces or not. Is by definition the expansion of T, the expansion of T generated by that. So the smallest expansion of T generated by that contains the Fn. Each Fn. So so well, maybe I'd say I just say the philosophy and I give a reference to the definition of a structure corresponds to a model in model theory. So the definition of a structure in model theory, and a really great book for this that helped me a lot to understand how that works is a book by Bakker. But what's really going on is that the way I think of it anyway, the super important thing is this axiom 4 that tells you that you can eliminate quantifiers. That's what it basically says. So and what you realize is that to give a structure is basically giving a model for logic, I guess. Okay, so now the super important definition. So a structure Sn is O minimal if, okay, two things happen. One, for all R in R, just the singleton is in S1. And also the set of X, Y in R2 such that X is less than Y is in S2. And the way they read this is that every singleton is definable, and every and just a set X less than Y is also definable. Okay, so those are two things actually which aren't always part of the definition, I think. For a logician in super general, which I'm not a logician, but for them, I think that this is not like, these are kind of what they tell us. Okay, but then the really important thing is that S1 consists of finite unions of intervals. Okay, so the definable subsets of R are just the finite unions of intervals. Okay, so that's really the important thing. So I think the first example in the like original version of the paper, I was saying it's like obvious, but then a friend of mine pointed out it's not obvious. I mean, it's ingrained in our thinking, I think. But Tarski's theorem says that the R-alg, the structure you get when you say the definable sets are the semi-algebraic subsets of Rn is O minimal. Structure where the definable sets are the semi-algebraic ones. Subsets of Rn is O minimal. And okay, actually it's the O minimal part is obvious because it's kind of, I think it's obvious anyway, that a definable subset of R, well, maybe it depends on how you put it, but it's kind of clear that a subset of R defined by a polynomial inequality is going to be a finite union of intervals. But what's deep is the quantifier elimination, like proving that R-alg actually gives you a structure. Okay, then much more recently, I think maybe a little over 20 years ago, Wilkie showed that showed the following. So let Rx denote the expansion of R-alg generated by the graph of the real, maybe I'll put this because this confused me the first time I saw it, the real exponential function. Like x, I'll just be super precise about this. X from R to R given by t goes to e to the t. Then R-alg is O minimal. Okay, and I'm going to even draw, for some reason in my notes, I drew a graph of the real exponential function. And actually, now I remember why I did it. Okay, so
do you mean Rx there, Patrick?
Oh, sorry, yeah, Rx, yeah, yeah. Oh, yeah, I switched, yeah, I don't, yeah, thanks. I went on like autopilot.
No, not there. Down below, up there, it's RL.
Oh, am I? No, it's Rx everywhere in this example.
No, the expansion of RL.
Oh, I see, yeah, oh, yeah. Oh, I see how, yeah. Oh, then I really went on autopilot. Yeah, Rx is this expansion of RL generated by the graph of the real exponential function. Then Rx is O minimal. That's what I wanted to say. And one thing, let me just point out. So if it's going to be O minimal, then by the axioms, if I stated the axioms, it would be clear that when I intersect with say a vertical line, I have to get a finite union of intervals. Okay, and it's kind of clear from the picture I drew, and that wait, the vertical, yeah, wait, that's clear for a function. Yeah, but what I want to say, sorry. Yeah, that's clear for any function. Okay, now what I want to say is when I intersect, sorry, let me draw it again. When I intersect with a horizontal line, I have to get a finite union of intervals. So no intersection with the horizontal line. Well, it's obviously, I mean, we know that the exponential function is 1 to 1. So it's the point is a point, in particular, a finite union of intervals. As it has to be for Rx to be O minimal. And the point I want to make, which is maybe stating the obvious, is that if we were to use the complex exponential function, well, that would not be true, because the intersection with the horizontal line would be basically z. So for the complex exponential, that doesn't hold. This clearly doesn't hold. So the expansion of RLs that you would get by adding on the graph of the complex exponential function, that wouldn't be O minimal. So expansion of RLs derived from adding on a complex exponential function is not O minimal. Just okay. Then there's another in the Hodge theory setting. There's another like further expansion that goes on, and that is this. So R and exp is the expansion of R exp gotten by generated by the graphs, of f. I think you just need from 0, 1 to R, where f is real analytic. And I think you have to, I'm not 100% sure, but I think that you have to, this function has to be, you know, real, it's like a germ of a real, I think real analytic can only be defined on open set. So you take it's real analytic on some open neighborhood, but this is also O minimal. Okay, having said this, maybe one surprising moral that I learned from thinking about this is that when you work with O minimal things, for a lot of it, it just doesn't matter what O minimal structure you have. A lot of things just are true in any, a lot of theorems are of the sort like that hold in any O minimal structure. But okay, let me say some jargon. So we say that f from A to B, where this is in say Rn and this is in Rm, is definable if its graph is in an O minimal structure. Whatever S if its graph is. Okay, so that the Rx is the smallest expansion of Ralt, where the real exponential function is definable, and this R and X is the smallest expansion of Rx, where the all these real analytic functions are definable, etc. Okay, so now I can state the Peterzil Starchenko theorem. Okay, so any closed analytic subset of Cn, which is definable in an O minimal expansion of R out, is algebraic. Okay, and maybe I say some, I say some remarks. Okay, one is that this is a crucial tool of BBT and BBK. That's Bakker, Brunebarbe and Tsimerman, and Bakker, BKT. Sorry. Bakker, Klingler, and Tsimerman. Okay, it's not the only tool, and it's actually not even the only tool that comes from Peterzil and Starchenko, but it is a crucial tool because in the end of the day, they're trying to prove that something is algebraic, and that this is the thing that they have factored all through. I mean, yeah. The other thing is that, okay, Peterzil and Starchenko, they give two proofs. Okay, one is a model theoretic, and it's actually of a stronger theorem. I mean, it's a more general theorem. I don't know, strong, yeah, it's just more general. And then the second proof is it is analytic. It uses results of Schiffman. So it uses results of Schiffman, which are actually kind of related to Bishop Stoll, but it doesn't use Bishop Stoll, and it's longer, I think, than what I'm going to say, which are related to Bishop Stoll. I mean, there's no logical relation, though. I think somehow Schiffman and Bishop Stoll were like working around the same time, and there's not really a logical relation. Okay, so now I tell you Stoll's theorem. Okay, okay, first I have to say the jargon. So HD, that's going to be d-dimensional Hausdorff measure. And I'm not going to give the, I could write, I mean, I don't remember the definition, but a Hausdorff measure is defined in terms of, it's defined for any metric space, X. So HD is a measure defined on any metric space. X in terms of like diameters of things, like diameters of covering. And there's a really, really big book by, on geometric measure theory by, I'm blocking the name, Federovich? No. The point, what I want to, so see geometric measure theory book.
Federer.
By Federer. And the thing I really need is that it just agrees with the usual definition of measure that we would give on kind of nice subsets. Okay, so having said that, so agrees with usual notion under good conditions. Which are verified in Federer. And having said that, here's Stoll's theorem, which is from, I think, the mid 60s or maybe early 60s. So suppose Z in Cn is a closed d-dimensional complex analytic subset. And suppose H, I guess 2D of Z intersect BR is O, big O of R to the 2D, okay, where BR is the open ball of radius R and Cn. Okay, and the big O is the big O notation. I don't know how to say that differently. So you're assuming that the intersection, the Hausdorff dimension of the intersection of Z with a big ball of radius R doesn't grow faster than some constant times R to the 2D. Then Z is algebraic. Okay, so it looks a lot, you notice it kind of looks a lot like Peterzil Starchenko, except that instead of definable, we have to check this volume condition. And when I was thinking about this, I thought, well, look at that volume condition. It probably doesn't hold just for, maybe 2 years ago, I was saying, like, well, the volume condition, it's probably more general than just any analytic subsets. It probably holds for any definable subset in an O minimal structure. And so, and that's not hard to prove. And I'll kind of sketch the proof. But then shortly after I posted the paper, I found out that, okay, it was proven in exactly the form I'm about to state it by Nguyen and Valette. And it was stated in a slightly different form that was for, what's it called, subanalytic subsets by Kurdyka quite a long time ago. I mean, like in the 80s. So Nguyen and Valette is kind of recent, and Kurdyka is, yeah, it's quite a long time ago. So here's the proposition. Suppose Z contained in Rn is definable in an O minimal expansion of R alge. Okay, then HD of C intersect the ball of radius R. And now Z is not complex analytic, so I don't have to do like the 2D. This is O of R to the D, where D is equal to the dim R of Z. Okay, so let me make a couple of remarks about this that might possibly be confusing. I mean, they've been confusing to people when I told them about it, and then I'll kind of sketch the proof. But first, I'll say from this you get a very quick proof. Get a very quick proof. I mean, you can almost. I mean, it's almost obvious quick proof of Peterzil Starchenko. I mean, you just, if Z is a complex analytic subset that's closed and definable, then this thing says that it satisfies the hypotheses of Bishop-Stoll, and you're done. The one thing that might confuse you, because if you're really, you want to be really careful with these things, you might wonder, like, what is a dimension? Okay, well, there's two possibilities. One is when you're working with Hausdorff dimension, there's always a dimension involved. The dimension, there's always a unique number where, what is it? If the D Hausdorff dimension is 0, then it has to be 0 for every number bigger than D. And if it's infinity, then it has to be infinity for every number less than D. And there can be only one number where it's finite. If there is such a number, finite and non-zero, there is such a number, that's the Hausdorff dimension. Okay, so that's one possible meaning of the dimension. The other possible meaning is that when you have a definable set, as we'll see, it has a very natural, definable and O-minimal expansion. It has a very natural dimension. The thing that lets us prove this theorem is that natural notion of dimension, because basically it's built up very simply from what they call cells. So that's how the dimension works. Okay, now I don't, since yeah, so now I'm always getting to the point where I'm like a little bit running out of time. So I want to tell you about sketch of the proof, but sketch of the proof requires cells. And actually, so the cells are the coolest thing. Or maybe I should also say that my proof is really, it's pretty much the same as the one that Nguyen and Valette gave, and probably the same as the one that Kurdyka gave too. So I have a way of thinking about cells. So, but maybe I should just give the formal definition. But like okay, I'll tell you my way of thinking about it first. So recall, like if you ever taught Calc 3, you talked about like regions. You call it like type 1 regions in R2. So from teaching Calc 3, which is multivariable calculus, if you ever did it, you talked about like type 1 regions in R2. So those are sets of the form S equals, so set of x, y, such that x is in some interval a, b, and g of x is less than y is less than f of x, where g and f, where I want this to be h. Sorry. H of x, where g and h are some nice functions. Okay, so this thing is a cell in R2 is a set like this where G and H are definable. So in this model theory, or the O-minimal model theory, a cell in R2 is a set like S where G and H are definable. Okay, except that I lied a little bit. Okay, I lied, a tiny bit lied. So one is, there's two obvious modifications. With two modifications. So which are kind of obvious. One, you have to allow yourself to switch X and Y. So you're allowed to switch X and Y. And two, Okay, I can't really say, what I want to say is you're allowed to take G and H to be the same, but then you would just get the empty set. But really, you add in graphs of functions on closed intervals. So you add in graphs of definable functions on closed intervals. Okay, so then when you teach Calc 3, you first integrate on R2, and then you integrate on R3, and for those you have to have what they call, I think, type 1, 2, 3 regions. They probably have I think it's type Roman numeral 1. So in R3, you also consider type, say, I'll call them 1, 2, 3 regions. Those are regions of the form so S equals X, Y, Z in R3, such that X, Y is in T, and G of X, Y is less than Z, is less than H of X, Y. Okay, when G and H are definable and T is definable, that's a cell. When G and H are definable and T is definable, that's a cell. And then cells in Rn are defined analogously. So obviously in R3, we also allow graphs of functions. So cells in Rn analogously. Okay, and also maybe some people might require, and maybe it's a good idea to require, G and H to be continuous. So can also require G and H to be continuous. And let's require that. Okay, so now what I want to say, so in R3, we like introduced maybe if you think about teaching Calc 3, you kind of feel weird because the mathematician, you're brought up to think that like there's a way more sets than these type 1 regions and type 1, 2, 3 regions that you might want to integrate over, and you know you're doing things in a kind of ad hoc way. The O minimal world is a paradise where every definable set is a finite union of cells. So maybe that's the theorem. So in an O minimal expansion of R alg, every definable set is a finite union of cells. So I don't know who proved this, but you definitely find it in Van den Dries. See Van den Dries. And there are a couple other things that are kind of important. So one is also the locus where any function is CK, that's definable. Locus where it's continuous is definable. I guess CK includes, if K equals 0, then includes continuous. So if H is a definable function, the locus where H is CK is definable, and dense if the domain is open. Okay, so in fact, you can, in an O minimal expansion, every subset of every definable set is a finite union of CK cells. So in an O minimal expansion. A definable set is a finite union of CK cells. So it's kind of really like a paradise. Okay, so having said that, since I'm kind of running out of time to give the actual proof of the volume estimate, what I'm going to do is draw a picture. So the actual proof isn't long, but I think like the way I kind of first thought about it is in terms of a picture, and I think my paper is kind of short, so okay, let's look at what I want to do is I just prove it in a special case where you look at the graph of the exponential function. And I think once you see that special case, it's pretty clear what's going to go on. So when you look at it, it goes like this. Over here is pretty flat. So the volume of this part of the graph is like a constant times the volume of this part of the x-axis. So if I intersect the graph with a ball, then the volume of this thing is really not going to be any different from the twice the radius of the ball. Over here, you don't have that, but instead of projecting onto the x-axis, you can project onto the y-axis, and then you do. That's the proof. I mean that's the heart of the thing. So the proof is really just project onto the x-axis when x is small and project onto the y-axis when x is big. So project onto x-axis when x is small and y-axis when x is big. Now I made it. You wanted to say this in a nice way. What I did, I used a Gauss map. I mean, so if you have a definable set, it's always, you can assume that it's C2 because you can break it up into a union of C2 cells, and then you can use the Gauss map to map it to the Grassmannian. And what sometimes confuses people, but it's pretty easy to see, the Grassmannian of like the K-planes in Rn, you can embed it as a closed submanifold of R to the M for some big M. I mean, you can't do that in algebraic geometry, but you can do that definably in R-alg. And then I just use the fact that like the map from S to the Grassmannian is like CK. If S is a CK cell, if S is a K, yeah. If S is a CK cell, then the map to the Grassmannian will be, maybe it's not CK, maybe it's like CK minus 2. But so in particular, I can reduce to the case where that map doesn't like stays inside some small, the image stays inside some small ball. So I can assume that the cell is like almost horizontal at all times, and then I'm basically reduced to this situation. So that's maybe all I want to say about that. Maybe, yeah, I'm out of time, so I'll stop.
All right.
Yeah.
Thank you very much, Pat. Any questions?
Yeah, this is Philip, Pat, that was very nice. And, the Bishop theorem and Schiffman, I remember that very well because that happened at Berkeley in the 60s. And what was behind a lot of that was the failure of the Bezout theorem for analytic subsets of, say, an affine algebraic variety. Famous example due to Bernie Schiffman shows it's a counterexample really to the Bezout type theorem measuring the order of growth of the intersection of two analytic varieties, bounding that by the order of growth of the two individual ones. So Eric Bishop was around at that time. The Stoll thing came later. I think that was, that grew out of a lot of the questions that came out of this, but it has a sort of interesting history, much of which is still open. I think the central question is this: if you have a projective variety, take out a hypersurface section of high degree, so you have an affine variety, then by Grauert, all of the cohomology of the projective variety in even degree becomes represented by analytic cycles on the affine. And the issue was to relate the order of growth of that analytic subvariety to the Hodge type of the original cohomology class on the closed projective variety. There's a lower bound, but the upper bound is equivalent to the Hodge conjecture. So there's a nice, interesting, and now, of course, completely unsolved whole set of questions centering around the theorem of Bishop and Stoll.
Yeah, I mean, I guess you wrote a paper about that, and also Kornalba and Schiffman wrote a paper about.
The Kornalba and Schiffman wrote the paper that gave the counterexample to Bezout in analytic geometry. I wrote a paper with Kornalba about relating the Hodge, if you like, the Hodge width of a cohomology class, giving a lower bound on the growth of the analytic variety that represents it in cohomology.
Yeah, I looked at, I think I looked at the paper. Well, I looked at both of the papers, but I'll tell you why I looked at Kornalba and Schiffman. But I maybe I should look at it more. So when I was thinking about this, what I wanted to do was to kind of remove even though I really liked the logic. I think the logic is great, but I wanted to remove it because I wanted to get analytic statements. So remove it from like Bakker, Brunebarbe, and Tsimerman. But the problem is that what I found that I needed is if I have two definable functions, definable analytic functions, I needed to know that their difference. So they need to know that the difference is going to be definable because they build some like sheaves out of them. But if I have two functions where the graph satisfies the bound of like Stoll or Bishop Stoll, I don't know how to prove that the difference would be also satisfy that bound. And that, so yeah, I mean, but I guess I was thinking that Kornalba and Schiffman might be related to that, but
yeah,
that would be one ingredient that you would need to imitate like what BBT are doing in a purely analytic way. Yeah, so I'll say that.
Other questions and comments? Well, if not, let's thank Patrick again for the wonderful talk. And so we proceed with June's talk tomorrow morning at 9 a.m. Thank you very much. See you tomorrow.